Before starting the thermodynamic analysis of our cycle, we need to define two kinds of things. First things are the assumptions we consciously make in order to do the thermodynamic analysis. And second thing are the input parameters of the problems in order to find all the other parameters from these input parameters. So let's discuss and detail each of these items before starting studying each of the transformations. First assumption we do is that we are at steady state. All the components are doing open transformation to the fluid, so with an inlet and an outlet for each of these components. We consider as usual that we are at steady state, so it means there's no storage of mass or of heat, and the inlet and outlet state of each of the components is at equilibrium and also independent of time. And then second assumption we'll do is that the working fluid, the gas that is undergoing all these different transformations, is an ideal gas. So it means that we will be able to apply the ideal gas law in any situation. And this is usually true for gas turbine cycle because the gas is very far from liquefaction conditions, so it is really behaving like an ideal gas. Another assumption we'll do, at least for now, is to consider that the thermophysical properties such as the Cp and Cv, so specific heat capacities at constant pressure and constant volumes, are constant, so independent especially of temperature, but also independent of any change of chemical nature that we can find. We'll do this assumption, and we'll discuss a bit later if this is really valid and how can we do without this assumption, but this will be discussed later. And then last assumption we'll do, and here in the specific case of the ideal juice cycle, is to consider the compression and the expansion to be reversible, so without entropy creation. So that's for the assumptions. Now the input parameters, what we know before starting the analysis. The first thing we have usually as input parameter is the temperature of point A, which corresponds to the temperature of the cold source. And as we will see later, most of the gas turbine cycle are open cycles. So here we have at the inlet of the compressor in A the air in atmospheric conditions. So it means it's in atmospheric temperature. And so the atmosphere would correspond to, from a thermodynamic point of view, to the cold source. Then similarly for the pressure of point A, which corresponds to the low pressure, low pressure in English, not like in French. To the low pressure, it corresponds also to the atmospheric pressure around 1 bar. So then what do we know? We usually know the temperature of point C, as we have seen before. That's the maximum temperature we have in the cycle, or it can be considered as the temperature of the hot source of the system. And what is fixing setting the temperature of point C in most gas turbine cycle? It's the mechanical properties of the turbine. It would give a better efficiency to still increase this highest temperature, but we set this temperature as the maximum that the material of the turbine blades can stand, and the order of magnitude will be 1400 or 1500 degrees Celsius for the order of magnitude of this maximal temperature. What else do we know? Then we know delta, the ratio of pressure between high pressure and low pressure. That corresponds to the ratio of pressure we have across the compressor, but also across the turbine. This is usually known because it's just a design choice when these elements are sized at the beginning when the machine is created. So this is considered as an input parameter in most cases. And finally, we consider that we know the thermophasic properties of the fluid, and these properties usually correspond only to the Cp and Cv of the air. And if we know both of them, we also know the Laplace coefficient gamma, which is just the ratio Cp over Cv. So with these assumptions and input parameters, now we can start developing the thermodynamic analysis of each of the transformations.